Good morning, everyone. Our topic is all about types of mechanical and periodic waves. So, let's define what is wave. So, wave is a vibratory disturbance that is transmitted through a material or space. So, the waves propagate from one point to another based on their properties. Each of the waves possess its own property based on its nature. So let's go to the types of or different types of waves. So number one is the mechanical waves. So mechanical waves is act as the propagation of a disturbance through a material medium due to the repeated periodic motion of the particles of the medium about their mean positions, the disturbance being handed over from one particle to the next. So example of mechanical waves is the vibration of string or etc. So the existence of a medium is essential for propagation. The method in which disturbance propagates with definite velocity without changing its form is called mechanical wave. So energy and momentum propagates by motion of particles of medium, but medium remains at a previous position. So the mass transfer does not take possible here. The propagation is possible due to the property of medium like elasticity and inertia. So example or types of mechanical waves is transverse waves. As you can see at the picture, the information of the crust through takes place. The direction of propagation of energy is perpendicular to the direction of oscillations. There are always two directions that are independent from each other that can be used as a direction of wave. So example of transverse wave is vibration of string. So another types of mechanical wave is the longitudinal waves. As you can see at the picture, longitudinal waves proceed in the form of compression. Here, compression and rarefaction, which is a stretched rubber band. For longitudinal wave at places of compression, the pressure of density tends to be maximum, while at places where the friction takes place. So, electromagnetic waves, properties of electromagnetic waves. In vacuum, electromagnetic waves travel with light velocity. It can be polarized. They are transverse in nature. Medium is not required for propagation the electromagnetic waves. It have a momentum. Example of this is radio waves, light waves, thermal radiation, and X-ray. So next is matter of waves. Matter of waves, these are also called the Broglie waves. They show or depict the wave nature of wave, like nature of all matter, everything that makes up our body, the atoms like. So that's the meaning of matter of wave. So my next partner will discuss about the periodical wave, and that's all of my topic. Thank you.
Everyone, my topic is about periodic waves or periodic motion. So, what is periodic motion? It is the same motion is repeated over and over before the vibration dies out. So, it is confined to a periodic variation of time and distance. We shall begin by examining the nature of the restoring forces. So, in the principle of Hooke's law, the big letter F symbolizes the restoring force is equal to negative K times X, which is the K is the constant and the X is the amount of deformation or change in length of object. So the minus or the negative sign indicates that the force is in the direction opposite to the deformation and tends to restore the object to its original shape. So, the formula, F is equal to the number of variation over the time. The small f is symbolize the frequency, which is the, so, for example, in figure 8.1, here, after the swimming jumps, the board vibrates up and down because of its elastic properties. The vibrating motion of the board is similar to the of so many vibrating objects that is useful to consider it in some detail. So here, the board is deformed from its normal shape. And there is an upward restoring force on the board, as you can see. So, the board has returned to its normal underform shape but now has an upward velocity. The restoring force following Hooke's law is 0, so the board continues to move upward. So in figure C, here, the board has moved above its normal position. The restoring force is now downward and the velocity of the board has been reduced to 0 by the restoring force. Here in the figure 8.1, letter D, the board has again returned to its normal position but now has a downward velocity. In the last figure 8.1, letter E, the board has moved below its normal position and the restoring force is accelerating it upward again. So the board and air assistance dump out the position. So as you can see in frequency and time, there are inversely proportion. So the time is equal to 1 over frequency and the frequency is equal to 1 over the time. The higher frequency, the less time each vibrates takes.
Good morning sa inyong lahat. Ang topic natin ay about mathematical description of wave to speed of transverse wave. So, sa mathematical description of wave, kailangan muna natin maintindihan yung mechanical wave and we will describe its properties mathematically. So, ano ba ang mechanical wave? Mechanical wave can be classified according to how the particles in the medium move relative to the movement of wave pattern. So dito sa mechanical wave, kailangan natin maintindihan din yung periodic wave. Ano ba ang periodic wave? Periodic wave is a disturbance that has a predefined rate of repetition. That is, the disturbance doesn't appear and then goes away. Instead, it continues to persist repeatedly with no end, with each disturbance consisting of an exact replica of the previous ones. So, sa periodic wave, ito yung picture niya. Makikita natin dito, ito yung wave, then ang tawag dito sa pagitan na to, wavelength, and dito naman, simula sa tuhod, ito yung amplitude na tinatawag. Now, there are two types of periodic wave, which is the transverse wave and longitudinal wave. What is transverse wave? Transverse wave, it is the transfer element direction perpendicular to the direction of the disturbance of the medium. So, although all points of wave are constrained to move only up and down, wave pulses move perpendicularly to the length of the string. So the next meaning is it may consist of more than one pulse. Sa transverse waves, consisting of many pulses result when the wave source oscillates about some equilibrium position for long periods of time. And these are the picture of the transverse wave. There is a wavelength, crest, amplitude, and throw. The crest, ito yun, it is the high point of wave. And the wavelength, ang amplitude, ito, yung pagitan nito. Amplitude, it is the maximum height of a rest or depth of a throw relative to the normal level. And then yung throw, ito yung the low point of wave. Then the next is the speed of transverse wave, which will be tackled by Kanina.
So, as Roma discussed to you yung wavelength, ako naman kung paano mag-compute ng speed of the wave. So, ang dapat, kailangan gamitin kapag mag-compute tayo ng speed of the wave, ang unit is meters per second or ganyan siya. So, di ba sabi ni Roma kanina, the two successive crests is equal to one wavelength. So, ito siya. Thus, ang magiging formula niya, speed is equal to distance traveled over time taken. Pero meron ding mga wave equation na medyo mas mapapadali tayo. So, ito nga. V is equal to wavelength in meter times F or in frequency in hertz. Okay. So, meron akong examples dito. Ayan. When a particular string is vibrated at the frequency of 10 Hz, a transverse wave of wavelength 0.25 meter is produced. Determine the speed of the wave as it travels along the string. So, kapag magkakamit ka, kailangan mo munang hanapin kung ano mga given. So, ito nga yung given, di ba? May frequency tayo, which is 10 Hz. Tapos, meron din tayong wavelength, which is 0.25 meter. So, ang i-determine natin is the speed of the wave, which is the V. So, di ba sabi ko kanina, ang equation niya is V is equal to wavelength times frequency. So, ito nga yun. So, substitute ko lang siya. 5 meter times yung F and HD. Diba ang unit na kailangan is meters per second? So, kailangan i-substitute mo dito. Ito. Ito, meter, as it is pa rin siya. Yung hertz, gawin mo lang siya second. So, times mo lang siya. So, ang magiging answer is 2.5 meters per second. Yun lang po.
Ayan, ang topic ko is speed of longitudinal wave. After nilang i-discuss, so first group, yung tungkol naman sa transverse wave, sasabihin ko muna sa inyo, ano ba ang longitudinal wave? Longitudinal wave, also known as L wave. Waves in which the displacement of the medium is in the same direction or the opposite direction to the travel of the wave. Ayan, as you can see nga nga dun sa example, ang wavelength is from left to right. Ayan. Or right to left. Puro left and right lang siya. Hindi siya nag-up and down. Or hindi siya pataas. Next, ano ba ang mga example ng longitudinal wave? As you can see, ilan sa mga example ng longitudinal wave is sound wave and pressure wave. Next, ano ba ang speed of longitudinal wave? The speed of a longitudinal wave is the same as the speed of transverse wave. Katulad nga nung equation nung una, kung ano yung naging equation sa transverse wave, yun lang din kung ano yung equation sa speed of longitudinal wave. Wave speed. Wave speed is the distance of a wave traveled per unit, per unit time. Next is the quantity. Ang quantity ng speed of longitudinal wave is wave speed at ang unit niya is meter per second. Next is speed of longitudinal wave equation. Ang equation is V is equal to wavelength times F, or V stands for the speed, wavelength, and F stands for the frequency. Example number 1, speed of longitudinal wave. The musical note A is a sound wave. That note has a frequency of 440 Hz and a wavelength of 0.784 meter. Calculate the speed of the musical note. Answer. First, you need to determine what is the given and what is required. As you can see, ang mga given natin is frequency, which is 440 Hz, and the wavelength, 0.784 meter. Next, ano ba yung kailangan mong i-determine or ano ba yung kailangan mong i-solve? Dahil meron na tayong wavelength and meron din tayong frequency, ang kailangan mong mahanap ngayon is yung yung speed, which is yun nga yung nasa-solve natin. Calculate the wave speed. Tulad nga ng given ko kanina, meron siyang para ma-solve mo yung speed, kailangan mo ng frequency times wavelength. Meron tayong given na frequency which is 440 Hz, and meron din tayong given na wavelength which is 0.784 meter. Para ma-solve mo, ita-times mo sila, kaya ang nakuhang answer is 345 meter per second, or 345 meter times second to the negative 1. Ayan. Next is wave speed word problem. A certain FM radio station broadcasts electromagnetic wave at a frequency of 9.05 times 10 to the 7 Hz. This radio wave travels at a speed of 3.0 times 10 to the 8 power times meter per second. What is the wavelength of these radio waves? Ayan, katulad nga ng sabi ko kanina, determine muna what is the given. Ang given natin is yung speed and yung frequency. Para ma-solve natin, kailangan natin hanapin yung wavelength. Ayan, so V divided by frequency para makuha mo yung wavelength. Ngayon, wavelength, para makuha mo yung wavelength, speed yun. Speed is equal to 3.0 times 10 to the 8 divided by 9.05 times 10 to the 7th power para makuha mo yung wavelength, which is 3.31 meter. Ayan, yan yung wavelength niya. So, yan yung part ko, speed of longitudinal wave. I-discuss nung isa pang reporter yung next, which is yung kanyang report. Yun lang.
So, yung topic ko is speed of sound waves in gases. So, I'll give you a short overview of what is sound waves. So, yung sound waves are longitudinal waves. Yun nga yung sabi kanina ni Celine, na example ng longitudinal waves, propagated through a material by the transfer of kinetic energy from one molecule to another. Hence, the velocity of the sound is greater in solid and liquids than in gases because the intermolecular forces in gases are very small or zero. So, punta na tayo sa aking pinaka-topic, which is the speed of sound waves in gas. The speed of sound in the gas is primarily a function of its temperature. Air is a mixture of gases and includes water vapor. The relative humidity of air has a slight effect on the speed of sound, while changes in air pressure has no real effect on the speed. Ayan nga, sabi dito, yung humidity, yun yung nakakapag-change ng wave ng sounds, yung speed ng sound waves. Kaso nga lang, yung effect is very slight lang, and yung pressure naman, wala talagang effect. So, ayan. The speed of sound in air is approximately 343 meter per second. Or sa ibang 1,130 feet per second or 770 miles per hour at room temperature of 20 degrees Celsius. The amount of humidity in the air increases the speed only small amount. Ayun nga. An extreme change in humidity is less than 0.5%. The speed of sound in air is usually simply measured in dry air. Ayan. So, punta naman tayo sa calculating the speed of sound wave. The speed of sound in dry air in meters per second is approximately equal to V is equal to 331.4 plus 0.6 TC meter per second, where V stands for the speed or velocity of sound, while TC is the Celsius temperature. Tapos, ayan, examples naman tayo. If TC or the Celsius temperature is equal to 0 degrees Celsius, then the V is equal to 331.4 plus 0. Kasi nga, diba, 0 yung degree Celsius. 0.6 times 0 is 0. Tapos, ayun nga, is equal to 331.4 meter per second. Another example is, if TC is equal to 20 degrees Celsius, then the V is equal to 331.4 plus 0.6 times 20 is equal to 331.4 plus yung 0.6 times 20, which is 12, equivalent to 343.4 meter per second. Then, speed in any gas. The speed of sound in gas is a function of temperature, the molecular structure of the gas, and its molecular mass. The molecular mass is the atomic weight of the molecule divided by 1,000. Ito yung mga example ng gases. So, ayan, speed and various gases. Pag gas, pag air naman, ang speed niya is 331. Pag carbon dioxide, 259. Oxygen, 316. Helium, 965. And hydrogen is 1,290. And that ends my report.
Hi, I'm Angelica Beatriz Chong and I'm about to discuss boundary of condition for a stream. Let us now investigate what happens when a mechanical transverse wave propagates along a medium and reaches the very boundary of this medium. The physical result when such a situation arises is referred to as a boundary condition. Now, let us begin with the definition. A boundary condition refers to how a traveling wave disturbance reacts and also what sort of transformation it experiences, if any, when this very disturbances reaches the boundary or end of the medium in which it propagates or travels. To understand what happens when we must consider two possible scenarios involving a rope model. We must consider what happens when the other end of the rope is tied or fixed in a manner in which it is not allowed to move. And we must consider what happens when the other end of the rope is freely allowed to move only vertically such that the tension property is not disturbed. Let us consider each of these boundary conditions separately. Now, let us proceed to boundary of condition with fixed end. The illustration shows what happens when an incoming or incident traveling transverse wave disturbance propagating in a mechanical medium reaches its boundary, where the end at this boundary is held fixed. The boundary condition of an incident traveling wave propagating to the right along a medium with a given velocity. The boundary of this medium is held fixed, resulting in an incident wave disturbance being reflected back in an inverted fashion. So here, this is what you call an incident wave or the incoming wave. So as it propagates in the wall where the end is fixed, it is being reflected, and now as a result it becomes inverted. Now, let's go to boundary condition for free end. This figure illustrates an incoming or incident traveling wave propagating to the right of our rope at a given velocity. Eventually, the traveling wave disturbance reaches the boundary of the medium, except the boundary conditions are much different with the free end than the fixed end. The first half of the wave disturbance has negative slope. Above, a positive upward force will manifest itself. But since the rope is allowed to swing freely, the effect that no transverse opposing force will be created. So the ring shifts up along the shaft. Then the ring will eventually reach a maximum height. At this point, the rope is stretched whereby the tension force takes effect. This tension, in turn, along with the positive slope, generate a downward force. So the end result is that the ring force is forced back down as if someone was physically holding the end of the rope and generating a new wave disturbance. The result in this case is that the incoming wave is reflected but no inversion occurs.
Hi, I'm Gian Jumay Bason, and I will discuss to you the principle of superposition. What happens when two or more waves pass through a same region of space at the same time? Will they produce large waves, or they will cancel one another? This topic is devoted to the descriptions of what happens when waves come together. So, there are many examples of occurring multiple sound waves, and examples are first the vocal sounds. These are the combination of waves of different frequencies, usually making a voice individually recognizable. The second type of sound waves are the musical instruments. They are designed to combine sound waves in such a way that it is common to make them more intense. The third type of sound waves are the echoes and reverberations. They are the very common kind of sound waves. The normal sounds are made up of many waves added together, even if the source emits only a single wave. So let's proceed to the meaning of the principle of superposition. Principle of superposition is the disturbance of the resultant wave is the sum of the disturbances of the combined waves. There are two types of the principle of superposition or the superposition. These are the constructive interference and the destructive interference. So this is the constructive interference. This is an example of constructive interference. As you can see, crests are positive disturbances, troughs are negative disturbances. So adding a crest through a trough tends to decrease the magnitude of the disturbance. This shows two waves having equal wavelengths and amplitudes superimposed crest to crest and trough to trough. When added waves produce a large disturbance, it is called constructive interference. As you can see, overlaps. It produces a large disturbance. Next is the destructive interference. In this figure, this shows what happens if the same two waves are superimposed crest to crest to trough, they cancel each other. When they produce a smaller disturbance, the process is called the destructive interference.
Good morning, everyone. I'm Arnett Crucia Garcia.
I'm Hannah Jane Estorija.
And we're going to report about the energy in wave motion. First of all, what are the wave characteristics?
Wave characteristics are the amplitude, wavelength, frequency, and period, then the wave velocity.
So, this is what we call the amplitude.
The amplitude.
And this is the wavelength.
Yeah. This is the wavelength.
Yes. And this pointed curve is the crest.
The crest.
And we have the equation for the wave velocity, which is velocity is equal to wavelength times the frequency.
This is the formula.
And now we're going to the energy transported by waves.
Just as the oscillation that starts it, the energy transported by a wave is proportional to the square of the amplitude. So the formula of intensity is the intensity equals to energy or time over the area or power over the area. So
This is the formula for the intensity. Energy over time all over area, or simply power over area. The intensity is also proportional to the square of the amplitude. If a wave is able to spread out three-dimensionally from its source, if a wave is able to spread out three-dimensionally from its source, and the medium is uniform, the wave is spherical. Just from geometrical considerations, as long as the power output is constant, we see that intensity is proportional to 1 over the square of the radius.
there we have it.
That's all.
Thank you.
Thank
Bye.
you.
Good morning, everyone. The topic we're going to discuss is about sound waves and resonance. So, what is sound wave? It organized vibration of air molecules. For example, plucking a guitar, string, voice, or the radio speaker. So, through plucking the guitar, from there, you will produce a sound wave. Resonance. Resonance is the force vibration of an object by a wave having natural frequency of the object. Another one, resonance is a physical property of an object. All physical objects resonate. Some have simple, uniform resonance patterns and some have complex resonance patterns. Some resonators are highly damped and some are weakly damped. Let's combine resonance and sound. Sound may be produced as a consequence of resonance patterns within an object, but sound should not be confused with resonance. For example, a guitar string of a fixed mass, length, and tension has a constant characteristic resonance pattern regardless of whether it is currently producing sound or not. Example, it is not vibrating or it is not within a vacuum.
So let's proceed to standing waves in strings. So when a string is fixed at both ends, example, guitar or piano, then the two ends are not free to move. When a wave front is reflected, it must reflect with inversion so that the resultant wave interference pattern always maintains zero displacement at each barrier. So, additional wavelength formula, lambda sub n is equals to 2L over n. So wavelength number 1, example, n is equals to 1, results in the value 2L over 1 or 2L, etc. Example, this figure is a waveform and the spectrum of the sound induced by the vibration of the high E string of a guitar. Standing waves in tubes. Uniform non-branching tubes can be classified into three types when determining standing wave patterns. Tubes closed at both ends, tube open at both ends, tubes open at one end and closed at the other. So calculating resonance wavelength and frequencies. So if we examine the standing wave patterns in figure number 10, we can see that the first four standing waves represents waves with 1/4, 3/4, 5/4, and 7/4 cycles within the length of the tube. For a tube of length L, this means that the first four resonance wavelength are 4L over 1, 4L over 3, and 4L over 5, and 4L over 7. If we know the speed of sound, we can calculate the frequencies of the first four resonances using the formula F is equals to C over lambda or wavelength. From which we can derive this formula equals for F over F or frequency sub n is equals to 2 times n minus 1 plus 1 times C all over 4L. Or more easily, we can determine the first resonance using F1 is equals to C over 4L. That's all.
Beats. This occur, for example, when two tuning forks with slightly different frequencies are sounded together, or when two organ pipes that are supposed to have exactly the same frequency are slightly out of tune. Consider a particular point in space where two waves overlap.
So there is also a motion within the wave itself. So for example, an ocean buoy moves up and down and back to the right or to the left as a wave passes. So our topic is all about the two types of motion within the wave itself. So there are the transverse wave and the longitudinal wave. So the transverse wave is when the motion of the motion within the wave itself is perpendicular to the travel of the wave. So, as in, the travel of transverse waves and longitudinal waves. So for example, earthquake, tremors, and ocean waves have both longitudinal and transverse waves components. So sound waves are purely longitudinal when it is in fluid, while waves on a string are usually transverse.
Good day. As a continuation of the two types of waves, I will be discussing about the longitudinal waves. So longitudinal waves are waves whose motions are parallel to the travel of the wave. So the wave is created by a forward and backward motion. So when the wave is pushed forward, then the wave is compressed. But when the wave is pulled backwards, then it produces the wave to expand. So it is said to be parallel because the movement or the motion of the wave, this one, and the travel of the wave is this one, and the movement of the wave is this one, making it parallel to each other. That's all. In real life, there are three types of earthquakes. The first one is this one. The one tectonic plate is moving the opposite way, parallel to the other one. So this is parallel to each other. The other one is tectonic plates tend to move away from each other, and the other one is tectonic plates move towards each other. Next is the ocean waves. So this is the ocean waves created when you are at the middle of the sea. So this is transverse. But when you are at the shore, it produces longitudinal waves because the waves are tossed towards the shore, then moves backward back to the sea. Next is the string. So let's say this is the string. When someone plucks the string, it produces transverse waves. So that's the relation of transverse and longitudinal waves to our daily lives.
The displacement of the individual waves at this point are plotted as function of the time in this figure. The total length of the time axis represents 1 second, and the frequencies are 16 Hz and 18 Hz. The 16 Hz is the blue graph above, and the 18 Hz is the red graph below. Applying the principle of superposition, we add the two displacements at each instant of time to find the total displacement at the time. The result is the graph of letter B. At certain times, the two waves are in phase, their maxima coincide and their amplitudes add. But as time goes by and they become more and more out of phase because of their slightly different frequency, eventually a positive peak of one wave coincides with a negative peak of another wave. The two waves then cancel each other and the total amplitude is 0. The resultant wave in letter B looks like a single sinusoidal wave with a varying amplitude that goes from a maximum to 0 and back. In this example, the amplitude goes through 2 maxima and 2 minima in 1 second. So the frequency of this amplitude variation is 2 Hz. The amplitude variation causes variation of loudness is called beats. And the frequency with which the loudness varies is called the beat frequency. The formula for bit frequency is frequency sub A minus frequency sub B. The bit frequency is the difference of the two frequencies. Remember that frequency sub A is the higher frequency.
Classmates, today I will going to discuss about Doppler effects. Doppler effect. When a source of sound and the listener are in motion relative to each other, the frequency of the sound heard by the listener is not the same as the source frequency. A similar effect occurs for light and radio waves. We'll return to this later in the session. Let's think first about a listener moving with velocity toward a stationary source. The source emits a sound wave with frequency and wavelength. The wave crest approaching the moving listener have a speed of propagating relative to the listener, so the frequency with which the crest arrive the listener's position. Now, suppose the source is also moving with velocity. The wave speed relative to the wave medium is still velocity. It is determined by the properties of the medium and is not changed by motion of the source. But the wavelength is no longer equal to wavelength.
We've probably experienced sonic booms caused by an airplane flying over faster than the speed of sound. We can see qualitatively why this happens from the figure that I will show later. Let Vs denote the speed of the airplane relative to the air, so that it is always positive. The motion of the airplane through the air produces sound. If Vs is less than the speed of sound in Vs, the waves in the front of the airplane are crowded together with a wavelength given. As the speed Vs of the airplane approaches the speed of sound V, the wavelength approaches zero and the wave crests pile up on each other. The airplane must exert a large force to compress the air in the front of it. By Newton's third law, the air exerts an equally large force back on the airplane. Hence, there is a large increase in aerodynamic drag or the air resistance as the airplane approaches the speed of sound, a phenomenon known as the sound barrier. We emphasize that a shock wave is produced continuously by any object that moves through the air at supersonic speed, not only at an instant that it breaks the sound barrier. The sound waves that combine to form the shock wave are created by a motion of the object itself, not by any sound source that the object may carry. The cracking noises of a bullet and of the tip of a circus whip are due to the supersonic motion. A supersonic jet plane may have very loud engines due to the supersonic motion. Indeed, the space shuttle makes a very loud sonic boom when coming in from a landing. Its engines are out of fuel at this point, so it is a supersonic glider.
The wave produced outside the body is focused by a reflector or acoustic lens, so that as much of it as possible converges on the stone. When the resulting stresses on the stone exceeds its tensile strength, it breaks into small pieces and can be eliminated. These techniques requires accurate determination of the location of the stone, which may be done using ultrasonic imaging techniques.